Okay, so I don't think anyone else has joined yet. So we're gonna start the meeting, and if people join, they can continue on. So this is the first lesson for Dynamic Planet by Vihan and I.
It's our agenda. So today we're just going to go over the rules, the homework you were supposed to do, uh, reminder for invitationals, how to,
And then we're gonna go over like the two topics.
yeah. So splitting up the work on the rules. So you and your partner should decide what parts of the rules each of you will study. Split up the work equally and study past what we go over in the meetings. So you have to study outside of the meetings. The meetings aren't enough. And look at the rules manual to do this step. This was homework as well, but nobody did. Very few people did the homework, so you get another chance this week to do it.
And then by annotating the rules you met, highlighting the exact parts you're splitting up between your partners. I know some people did it, but not everyone did it. So like, please do that in the future. But like, split up who's doing what topic, and then compile it in your notes so that both partners have access to it in the binder. Also, a reminder: an invitational is coming up very soon. I think 2 weeks as now. So get all of your work split up and finished before the invitationals. Like all the notes, practice tests, all that should be done ASAP. And then you should finish. You should have at least 2 days before the competition to like print all the notes and then read through it, review it, and maybe take a few practice tests. That should be the general timeline.
Okay, so creating a Word doc, we highly recommend that you take your notes online. It's just way easier, preferably on Word. That's how most people do it. It makes it much easier to format and edit notes throughout the season for competitions. So first, just take a screenshot of the rules manual and add it to your document at the front, just for reference. Second, number the pages so you can have an index in the front for where to find each thing. So numbering pages is useful. And then images are the key to this event. Images for your things are really important.
Yeah, like in the glaciers specifically, there's like a lot of like parts of the glacier, types of glaciers, name of some specific types of glacier. So like having images will be very key. Wait one sec. Abhinay. Abhinay. नहीं निकलो. Bye. Okay, anyway, so yeah, images are very important because many of the questions are classification based. So that's important. Also, along with numbering the pages, uh, make sure to like create an effective table of contents and also create tabs for the exact pages so you can easily go through it. Because you in the actual competition, you'll have very less time to go through your notes, and most of it should be easily manageable or memorized. So this is an example of a table of contents. Like this is my table of contents for this year's Dynamic Planet. So as you can see, these are the main topics, and then there's subsections. So it's easier. So I have the page number, so it's easier to go to the exact page and manage everything.
Okay, so today we'll be covering all of session A. Follow along, listen, and take notes.
Yes, please take notes. This, although it's kind of just surface level, make sure to take notes. Add it to the actual Words document that you have, and then research more and add on.
So the properties of ice. So there's density and crystal structure and density. It is there's a specific thing at 0 degrees Celsius and standard atmospheric pressure, which means that it floats in water. It has specific density. And for crystal structure, ice has a hexagonal crystal lattice, meaning that water molecules arrange themselves into layered hexagons upon freezing. And then so there's lower crystal growth in lower and in colder and drier atmospheres, creating more hexagonal symmetry, possibly creating hexagonal prisms.
Okay, so there are many properties of ice. So continuing on, there's mechanical and thermal. So mechanically in ice, ice has elastic deformation under stress, so it like goes to the original state after the stress ceases. And when there's shear stress or force applied to the ice for a long time, the sample will deform elastically in something known as plastic deformation, and this permanently deforms the shape. So this is involved in in creep and intracrystalline gliding. We'll talk about more of this in later slides. So then, intracrystalline gliding is basically layers within the ice crystals that shear parallel to each other without destroying the continuity of the lattice. And then also recrystallization is when the crystal boundaries change in size and shape based on the adjacent crystals exerted stress. Another main part about the properties of ice is when you look at it thermally. So it includes the heat of fusion of water, which is the heat absorbed melting the ice at 334 kilojoules per kg, which is a specific heat, specific heat is basically the amount of heat needed to raise the temperature of 1 gram of a substance, so like in this case ice, by 1 degree Celsius, at freezing point being 2.04 kilojoules per degree Celsius. So, and then there's also thermal conductivity. So thermal conductivity is the ability for the ice to actually conduct the heat, make sure like the heat goes through it from one place to another while the material moves, at freezing being 2.24 watts per meter Kelvin. And the lowering of the melting point due to hydrostatic pressure is 0.0074 degrees Celsius per bar. So the hydrostatic pressure is outward pressure exerted perpendicular to the ice's surface.
Okay, and then the last property is the optical property. So ice is transparent, as you probably know, having through air bubbles, it makes it more opaque. Having an absorption coefficient, rate at which the incident radiation decreases with depth, is 0.001 centimeters raised to the negative first less for clear ice, and 0.1 centimeters raised to the negative first for snow, being weakly birefringent, doubly retracting, meaning that is light in transmitted at different speeds in different crystallographic directions, and absorbing red wavelength light, causing scattering light from glacier crevices to look blue-green. And the albedo of snow is 0.8 to 0.9, having one of the highest albedos, and being highly reflective but decreasing with age. Albedo of ice goes from 7% for open water to 85% for snow-covered ice.
Essentially, albedo is basically how much sunlight is reflected by the surface. So having a high albedo means that the ice reflects it much better. So now we'll talk about the formation of glacial ice from the actual snow. So there are two types, neve and firn. So neve is young snow that is hard and granular, forming from partial melting, refreezing, and compacting. And it forms in the surface part of the upper end of a glacier. And then after that, there's firn. Firn is essentially neve that survives a full season, which is one whole annual melt season. And it's basically essentially becomes glacial ice. And it's a type of snow that's been left over from past seasons and recrystallized into a substance denser than neve. And it also refers to the zone of accumulation, which we'll talk about in the next 2 slides.
So glacial budget and mass balance. So glacial budget describes how ice accumulates or melts on a glacier. If there's more accumulation, the glacier advances, while if there's more melting, the glacier retreats. Zone of accumulation is the zone where ice is accumulated. Input snow exceeds output melting. The zone of ablation was the zone where ice melts, where input snow is less than output melting. Head is the upper end, or the beginning of the glacier, while the terminus or snout of the glaciers is the toe, or is the glacier's leading edge based on the summer melting.
Okay, continue on. There's something known as the equilibrium line. So that is essentially the boundary between the zone of accumulation and ablation. So basically, as you saw here, accumulation is this top part, because that's where more snow is, and ablation is the bottom part, where there's more melting. And this equilibrium line separates both, essentially. So In the winter colder periods, the line moves downwards because if you think about it, there's going to be more snow accumulation, so the zone of accumulation will be much, much bigger. So the equilibrium line will go downwards. While in the summer or warmer periods, it moves upwards since there's more melting and thus a bigger zone of ablation. Below the line, bare ice is exposed since last winter's snow has melted, and above the line, the ice is covered with snow from the previous winter since it's accumulating. Another important term is net balance, which is the difference between the total accumulation and ablation in 1 year, and it's the annual change in ice store. Dynamic equilibrium is when the output melting is the same as input snow accumulation, and it's essentially at an equilibrium. The glacier, however, still moves downhill due to being in a state of continual transformation.
Okay, glacial flow. Glacial flow is movement due to gravity. Glaciers cannot flow independently on level ground or over uphill terrain until they're over 60 meters thick. Glacial flow is different from advance or recession, mass balance, since flow backwards up the glacier, but can have loss of ice at terminus to make it appear higher up. Glaciers, ice deformed under gravity, move downslope, always through the accumulation of ice in upper portion and melting in lower portions. Glaciers discharge ice from accumulation to ablation area, with the balance velocity being controlled by mass balance and the glacier's geometry. They move through deformation and sliding, with resistive stress controlling the flow downslope. Glacier flow, velocity, and motion is controlled by ice geometry, thickness, and steepness, ice properties, valley geometry, bedrock conditions, hard, soft, frozen, or thawed bed, subglacial hydrology, terminal environment, mass balance.
So there's some other factors that affect glacial flow, including bedrock conditions and its friction being a force against the actual flow of the glacier, because friction makes it slower. Terminal conditions, such as the terminal moraine, which is essentially a bunch of sediment that accumulates at the end of the glacier, provides buffer for the glacier movement. Another type of glacial, there's something else known as ice shelf buttressing, and it's when an ice shelf, which is a type of glacier, prevents an outlet glacier, which is basically glacier in sort of a valley, from advancing into the sea. So it stops that flow, and this is critical to the stability of ice sheets in Antarctica and Greenland. Glacial flow happened because of permanent deformation from strain and from stress. So strain is, if you don't know, strain is the deformation of ice or sediments at an ice bed interface or sliding at the ice bed interface. And resistance to strain depends on ice temperature, crystal structure, bed roughness, debris content, and water creep. Another type of glacial flow is creep, and it's the deformation of ice crystals with movement happening between the actual ice crystals. There's something known as Glen's flow law, and it's the relationship between the creep and stress, with glacier ice forming beautiful folds and structures in response to the creep. Brittle deformation is when the creep cannot happen fast enough to accommodate driving stresses. Brittle failure is an example. An example of brittle failure is crevasses, which are these small openings in the actual glacier. Thrusting is compression of margins at the glacier and is a fault in ice due to brittle deformation. And the deformation of bed depends on pore water pressure, which is poorly drained subglacial sediments that are saturated with water and create high pore water pressures. And if those are similar to the ice overburden pressure, then normal stress acts between grains to reduce the normal stress.
Okay, internal or plastic deformation. It is also known as creep or internal flow. It is when ice crystals slowly slide across each other within glacier. Ice can deform because it behaves plastically with extreme pressures, standard conditions. This occurs in all glaciers not reliant on meltwater. Glaciers flow faster near centers due to internal deformation, such as ice can slide readily against other ice than rock beds, leading to a sagging shape.
Okay, basal sliding. So basal sliding is movement of the base of the glacier, which is the ground, and it's where meltwater essentially helps the glacier move. So thinner, steeper glaciers are the most active when comparing glaciers undergoing basal sliding. Sliding velocity is controlled by basal shear stress and effective pressure, which is the difference between ice overburden pressure and water pressure. Basal slip is when there's a thin layer of water between the ice and underlying rock, lubricating the glacier essentially to make it move faster since there's not much friction. And basal slip also happens in more smooth bedrock surfaces. With enough meltwater, surges can occur from the basal slide. So there's something known as an enhanced basal creep, which is when ice encounters a large obstacle like this here, and with the large increase in pressure causing ice to deform plastically around an obstacle. A second type is known as regulation flow, and it's when ice encounters a small bedrock obstacle, which is this image, but instead of deforming it, the ice melts under pressure over here, and then it goes over the mound and refreezes on the other side. So that's essentially how this regulation flow works.
So subglacial and or bed deformation. It is the shifting of soft sediments, subglacial till made of unsorted sediments from boulders to clay, with finer sediments like clay and sand deforming readily when shear stress or when there's high power water pressure due to not being cohesive, high pruned water pressure to allow glaciers to go downhill. Depending on meltwater, while basal sliding is efficient if water is underneath surface of ice, bed deformation is prevalent when sediment is saturated with water to reduce its strength.
Okay, now there's something known as the thermal regime, and it's the temperature at the base of the glacier that determines that is a method of classifying glaciers, and it's important for basal sliding and subglacial deformation. So there are three types: polar, warm base, and subpolar. Polar is when it's frozen the entire year except for seasonal melting. So the base is frozen, there's no meltwater, and ice is frozen to the rock. And it's found in higher latitudes like the polar areas. And these glaciers move through internal deformation. Second is warm base slash temperate slash wet base. And it's warm enough for meltwater to actually form. And it's close to melting point during the year through the entirety of the glacier's thickness. It's found in a bit of a lower latitude than the polar regions, and they move through basal slip and basal sliding with meltwater from the surface melt channeling to the bottom through structures known as moraines, tunnels, and crevasses, which we'll cover in future meetings, and they're substantial to the process. Basal ice melting can cause more basal slip through temperature or pressure melting. And during winter, glacier refreezes to bedrock, slow movement periodically, with meltwater leading to more plucking, which is when the glacier essentially takes in sediment from the ground, not without meltwater. Finally, there's subpolar, which is when there's warm and cold glaciers varying from location, and most valley glaciers are polythermal.
Okay, stress and strain. Stress is how hard the material is pushed or pulled from external forces, while strain is the amount of deformation due to the stress. Force is a type of stress, as it changes the motion of a mass through push or pull. Stress acts as right angles to a surface, normal stress, or parallel to a surface, shear stress. Two tractions are acting parallel to the surface, and in the case of a glacier, the gravitational driving stresses are resisted by basal plate motion driven by friction between convection currents in the asthenosphere and lithosphere, and lateral drag, resistive stress when glacier flows against valley walls from friction. Strain is the change in shape of the object following stress. It may be elastic, temporary change in material, with material reverting to original shape after stress is removed, with change in shape storing strain energy, or permanent, when strain energy is released at certain levels of stress, causing this failure slash permanent deformation. With the level of stress at which the failure occurs being the yield stress, it can be brittle, where material fractures, or ductile, where flows or creep occurs.
Okay, so continuing on, there's two types of stress. There's three types of stress actually. So basal shear stress, and this occurs at the base or the bottom of the glacier, where there's minimal slope. and the normal stress acting on the base is based on the actual weight of the entire glacier. This means that stress increases as ice thickens. Basal shear stress causes strain, deforming ice, and causing glaciers to flow. This stress varies across glacier bed, since glaciers do not flow on hard, smooth surfaces and have some areas of higher or lower stresses on a rough bed. Basal driving stress is 10 to the 5 pascals at the base, and this uniform stress is due to ice deforming through non-linear viscous flow, and an effective viscosity that lets ice to support basal shear stress at 10 to 5 pascals. Second, there's longitudinal stress, which modifies the basal shear stress and is essentially the pulling and pushing effect of ice. As ice becomes faster, there's more tensile stresses, and it decelerates, there's more compressional, as in it comes together. This causes the brittle fracture of ice, which forms something known as crevasses. Finally, there's transverse stress, which is lateral drag against the valley walls for a valley glacier, or slow moving ice for an ice surface. Vertical shear stress gradients is when there's an extensive shearing at the bed or the bottom, and limited shearing at the surface or the top. Vertical resistive stresses are important where flow regime changes, ice divided margin, but it's smaller than the other stresses.
So, as for your homework, not many of you finished last week's homework. So, while it will be considered as not complete, we are still requiring that you send your annotated rules manually to us on Outlook. By annotating, we mean that you go through the rules with your partner, highlight which sections you will be splitting between you two. This is a top priority. Do this ASAP because your invitationals are soon.
Okay, 2. Finished notes for this section. So, not many of you clearly did not join this meeting. And also, we kind of rushed through this a bit due to time constraints. So, you might have not understood this completely. So, we expect you guys to continue researching on this, go more in depth, and finish notes for Section A by the next meeting. And on that note, meetings are not every week, but rather every alternating week. So, the next meeting will be on the 20th. So we want you to have the rules copied in the first 2 pages, a table of contents with page numbers, and then your actual notes with a lot of images. So we want you guys to send this to us via our emails, which is these 2 on the right. So please do that by the time we told you guys to. Also, this was an overview, so please remember you need a lot more research. And with that, we're done. So if you have any question, you can ask right now.
Wait, can you send the PowerPoint in the thing so we can review it?
Yeah, we're gonna do that.
Yeah, we're also sending a screen recording of the meeting.
Yeah. That's it. I guess we can end for today. So, regularly meetings will be 1 hour. This one was much shorter because there wasn't as much content and there weren't as many people for questions. But yeah, I guess that's it for today. So bye guys.
Okay, that's your
Bye,
stuff
thank you.
done.